and then the desktop code font, which gets, desktop code font, which gets used in the command window, I can bump that up to a much larger font. So how is that? Is that easier to read for people that size?
Well, that's much better.
Yeah. Okay, you go to Preferences, Fonts, Desktop Code Font, set the size. So I moved it from 10 to 18.
Beautiful.
So now that should make it a little bit easier to see what I'm doing when I'm up there. So today is going to be a little bit different from the last few because we're moving into the topic of linear algebra. Unfortunately, not all of you are going to have had linear algebra before, so I'm going to try and cover just brief outline of a lot of the linear algebra topics that we can use in MATLAB. So I'm going to be focusing on the numerical applications. If you take the linear algebra class, you'll get a lot more of the theoretical and out to the nth power kind of stuff. This class we're going to focus on just the specific numerical. So let's start with vectors. At the simplest, a vector is just an ordered set of values. Each value in that ordered set represents some distance in a direction. So you may have seen a vector that looks something like this. That's using our standard Cartesian coordinate systems, and in this case we have unit vectors that tell us which axis each distance is taken along. Now MATLAB doesn't have unit vectors, so it's just all defined by position. So this vector in MATLAB would be drawn as just 3, 4, 5. That should not be a squiggly bracket. And so in this case, you have one axis that is your first column, an axis that's your second column, an axis that's your third column, and whatever the value in those places of the vector are, that is your distance along that axis. So what a vector does, it basically takes some origin point and defines a point in space with reference to that origin point. So, in general, that's the simplified form. In general, you can go out to n terms. So, and however many terms you have, that is the dimension you're in. So if I were to, say, define v1 to be, what did I use here? 1, and I can just use spaces or commas in MATLAB. I'll use commas to keep it clear. 4, 8, 2. This is a 4-term vector, so it's in the 4th dimension. So vector operations, addition and subtraction are fairly simple. It's just term by term, add them together. So I'll define v2 equal to 8, 5, 1, 7. So if I add these together, it'll just take the first plus the first, second plus the second, and so on. And that's just standard. Whoop. We need to put an equal sign. And so that gives me my sum. I do the same thing with subtraction. v2 minus v1 gives me each spot subtracted. Now, scalar multiplication, I'm going to use the term scalar a lot. That just means a single number. So if you multiply a vector by a single number or a scalar, it multiplies every point in that vector by that scalar. So if I took my v1, let me just blow this up so you and then I multiply my v1 times 4, I get each point of the vector multiplied by 4. MATLAB does something, this isn't an actual mathematical operation, but MATLAB also allows for scalar addition and subtraction. If I were to say v1 plus 4, it would add that scalar 4 to every point of the vector. That's not normally a mathematical operation, but sometimes you want to do something like that, and MATLAB makes it, just has that as shorthand. So that vector is now 4 plus every point of the initial vector. So you can't multiply vectors like you can scalars, but there are a couple of special forms that you can use. And the first is called the inner product or the dot product. And for that one, it's also term-wise, but it multiplies each space of a vector and then adds them all together. So for MATLAB, the command is dot. So if I do dot v1, v2, this is going to return a scalar value because it's going to take the first position times the first position plus the second times the second, and so on, add it all up. And so that will give me, in this case, a value of 50. There's another form of vector multiplication that you don't really get into in linear algebra. It gets used a lot in vector calculus and the fields that rely on vector calculus, so engineering, dynamics, mechanics, physics, mechanics, electricity, magnetism, field calculations, and that's the cross product. We're not really going to do much with it, but you can, if I were to just do, find a couple of.
Where's the 50 come from?
The 50 is the dot product or the inner product of the vectors. So the way it works, if I have this vector and some v2, I'm not going to use the same ones as I did there. So if I take the inner product or the dot product of these two vectors, I multiply these two, so it'd be 3 times 1 plus the product of these two, 4 times 7, plus the product of these two, 2 times -5. Multiply each of these, add them up. That is the dot product. That's where that 50 came from. So if you actually were to do this in, which now that I say that, oh yeah, duh, because this was different vectors. So in this case, the dot product would be 3 plus 28 minus 10, or 15. So that also gets used a lot in vector calculus, but it also shows up in linear algebra. You'll talk about inner product spaces and various applications of that to linear. So I don't think I'm going to bother with the cross product because, again, we're not really going to use it. But if you're taking one of those classes that you do have to use a cross product, you can use the cross, put in your vectors, hit enter, and it will give you the cross products of those two vectors. So finally, a couple of other things you can do with vectors in MATLAB is length and norm. So you think length and you think, well, how long is the vector? MATLAB doesn't think that way. For MATLAB, the length is what dimension you're in. It's how many places there are in the vector. So if you remember, both of our vectors here, v1, v2, they were 4-place vectors. So if I were to use the command length v1, it will return 4. That's how many places there are in vector v1. For the actual physical length, the distance covered by the vector, you use norm, N-O-R-M. So if I take norm of v1, that will return 9.22, which is the actual length of that vector from the point of origin to the point in space that it's looking at. And something important to note that for all of these, for vector addition, subtraction, the inner product, all of these, the vectors have to be the same number of places. You can't add a 5-place vector to a 3-place vector. You can't take an inner product of a 5-place and a 3-place vector. So finally, just a quick touch, because this is going to get important later, and that is linear independence. So again, all of these vectors, you can picture them as being lines in space. And so if you want a vector to be what's called linearly independent of another vector, it has to mean that it's not traveling the same line. So if I wanted to create, well, call it, let's take a look at my V1 again. So if I wanted to create a vector that's linearly dependent on V1, I could just change the signs of all of those. So -1, -4, -8, -2. This vector is just V1 in the other direction. So it's all I have to do to get V1 back out of there is take my VDEP and multiply it by -1. And I get the exact same vector. So that's what linear independence is as long as you can't make up one vector as a sum of the scalar products of other vectors, they are all linearly independent. So that's going to be important in just a little bit when we start talking about certain aspects of matrices. But first, let's talk about what is a matrix. A matrix, its most simple definition is just a rectangular array of numbers. You have some number of rows, some number of columns. Each row-column intersection has a number in it. So earlier, we could draw sort of a generalized vector form as being, so you have some vector being your set of values V1, V2, V3, all the way to some Vn. These subscripts have nothing to do with the value, they're just an index. They say what place in the vector that holds. So when you have now a matrix, some matrix A, now you have basically a collection of vectors. Each row of your matrix is going to be some vector. So now you have now you have a double index because you have your row position, but you also have your column position. So then your next value is going to be still first row, second column, all the way out to first row and some nth column. And as you go down, you have second row, first column, all the way down to some mth row, first column. And if you recall, this double indexing system, so any point in this matrix can be described as being the point A, ij, where I is your row and j is your column. And if you remember, this is actually how MATLAB can access specific portions of a matrix. So if I wanted to just create a random matrix here, make a 6x5 matrix, and then I wanted the value at, say, the fourth row, third column, I can access that by using A parentheses 4 for row, 3 for column, and that will give me 2, which is that value of 4th row, 3rd column. So in this case, it's a fairly small matrix. You can just look it up. But if you remember from last week when we were using matrix representations of images where each place held 1 pixel of an image, we had hundreds of thousands of positions in this matrix. And that's where you can't always go and hunt for it. You want a quick command that can look up or even alter a specific value in that matrix. So we just talked about how with vector you can take length and that will give you the number of terms in the vector. So for matrices, you use the size command. So if I do size A, that will give me the number of rows followed by the number of columns. So this was a 6 row by 5 column matrix. So if I type size A, it returns 6, 5. And that can be important because just like with vectors, adding and subtracting matrices is done on a term-by-term basis. So let me create a new A here that's a little smaller, easier to work with. So I'll use 1, 2, 3, 4. And note that when you're making a matrix, commas separate columns in a single row, semicolon tells it to start a new row. So that's going to be 1 matrix and B equal to 8, 7, 6, 5. So now I have my 2 matrices to work with. So if I add A plus B, again, it will go term-wise, just add them together. Subtraction works exactly the same. Scalar multiplication, scalar addition, all of these work the exact same as they do for vectors. There is also an option with matrices called array multiplication or array division or array exponentiation, where each term in the matrix is multiplied or divided by that corresponding term in the other matrix. So if I were to do A dot star, which tells it to do array multiplication B, that would fill each position with the product of the 2 numbers in the 2 positions of that position of A and B. And I can do the same if I wanted to, say, take A and just raise every value in A to the power of 2. I can do the dot caret 2, and that will square every value in A. So this matters because actual matrix multiplication is different. It's a lot more complicated. And that's one of the reasons I went over what we just talked about with inner product. Because when you multiply 2 matrices together, you're essentially taking the inner product of the first row of the first matrix and the first column of the second matrix and putting that value into the first position of the new matrix. So again, using our A and B that we have here, when I actually matrix multiply these, if I do A times B, it's going to take that inner product of the first row and the first column here and put that into the first position of the resultant matrix, and then so on. Second column, second row, first column goes into that position, second row, first column position, and so on. So if I were to do just A times B, that gets us a very different answer than if you remember up here when we did the array multiplication, we got 8, 14, 18, 20, but down here we get 20, 17, 48, 41. And in this case, unlike most cases of multiplication, you can't change the order and get the same answer out. So if I were to do B times A, see, I get a different matrix entirely. And because of the ways, because it's going row by column, you don't have to have the exact same size matrix. You have to have a matching number of columns of the first matrix and rows of the second matrix. So if I were to create a new matrix C and D, so in this case, note these matrices are not the same size. If I were to try and add these matrices, subtract them, whatever, it wouldn't work. In fact, let me just see what happens. C plus D, sorry, matrix dimensions must agree. It's not going to let me do that. But because matrix C has 3 columns and matrix D has 3 rows, I can still multiply them. So if I do C times D, that gives me a square matrix because the product matrix takes its number of rows from the first matrix and its number of columns from the second. So you can look at it as number of rows of the first goes to the product, number of columns of the first and number of rows of the second cancel each other out, and the number of columns of the second defines the number of columns of the resultant. So that is matrix multiplication. Matrix division does not exist. Let me say that again. Matrix division does not exist. I emphasize that because we're going to use something in just a little bit called inverse, which looks a lot like matrix division, but it's not. That doesn't exist. So a couple more, before we get to that, a couple more things you can do with these matrices. The transpose of a matrix just swaps rows for columns, columns for rows. So if I take that matrix C there, the transpose will have 2 columns, 2 rows, 2 columns, 3 rows, and the first column will be the first row of C, the second column will be the second row of C. So MATLAB, that command is use the single apostrophe.
I'm working a full-time job.
So that gives the transpose of a matrix. And then lastly, augmentation is where you combine 2 different matrices into one. To augment 2 matrices together, they have to have the same number of rows, because basically you take one matrix and stick the other one right next to it and make one big matrix out of that. So in this case, let me give my C trans an actual variable. And so now, because this C trans here and D have the same number of rows, I can augment them together just using square bracket C trans space no comma D, and see that gives me now a 3 by 4 matrix where the first 2 columns are the 2 columns from C trans, and the second 2 columns are the 2 columns from D. And there's certain processes that we use when solving systems of equations where you have to augment two matrices together and operate on the combined matrix.
So the C prime, that was the transpose of C.
That's the transpose of C.
And then what is C trans D?
C trans is just the variable I, because C prime, that prime mark is an operator. So at this point, that matrix just existed as the answer variable, and I wanted to assign it to a named variable. So I called that C trans equals the transpose of C. And so now the variable C trans holds that value, because otherwise every value from the regular calculations gets held in the answer variable and gets wiped out the next operation you use. So there are a few special types of matrices that will come up. First is the zero matrix. The name is descriptive. It is a matrix that is filled with zeros. In MATLAB, you can create a zero matrix by using zeros and then define the dimensions you want. So this is going to create a 4x3 zero matrix. And if I just put a single value in there, it would give me a square matrix with each being that. This is something that will come up probably a good deal as you're writing functions and programs, because these zero matrices are a great way to store data. You create zero matrix as an empty holding space and then fill it space by space with the output of whatever function you are working with. Sometimes you don't want zeros, you want ones. It's exactly the same. This time I'll do 3, 4, matrix full of ones. And then the last one, the special one, is the identity matrix. The identity matrix has a row of ones along its diagonal and zeros everywhere else. And it is always a square matrix. And the unique thing about the identity matrix is it basically functions as the one of the matrix world when it comes to multiplication. Any matrix times the relevantly sized identity matrix equals itself. So let's go back to using D. So if I wanted to multiply D with a square matrix, I need something that has two columns. So to create an identity matrix, you use, I'll call it I, you use the command I, like the I in your head, EYE, and then the dimension of the identity matrix. So you see here it's